Hi everyone. We are going to discuss about the comparison of strength of treated clay using lime. Our team members are Rose, Ajit, Akshay and myself. What is the need for soil stabilization? Soil stabilization increases the bearing capacity of soil. It protects the soil from weathering. It also increases the soil's permeability. There are various processes for soil stabilization. It includes physical, chemical, and certain mechanical processes. In this, we use the chemical stabilization procedure, in which the chemical properties of soil is changed by use of admixtures as lime. The various type of lime used for soil stabilization are hydrated high calcium lime, monohydrated dolomite lime, calcite cuke lime, and dolomite lime. Why we use lime as soil stabilization? Lime stabilization improves the strength, stiffness, and durability of fine-grained soil. It is effective in heavy clay soil. It also reduces the liquidity limit and plasticity index of soil. Lime produces the maximum density and a high optimum moisture content in untreated soil. It is useful in highly unstable plastic and swelling clay. It is one of the cheapest soil stabilization methods. What is the effect on lime in soil? Due to the pozzolanic reaction, there is a long-term strength that is achieved for the soil by addition of lime. It is shown graphically in the above. Moving on to the next slide.
In this slide, we will discuss the strength parameters of soil. The most important strength parameter of soil is shear strength, which is the resistance of soil to applied shearing force. The peak strength as the strength parameters refers to the highest shear stress level relative to average stress within soil as seen in the graph between shear stress versus the displacement. Based on more Coulomb criteria, the shear strength depends on normal stress and internal friction angle C and phi, which is represented as tau equal to C plus sigma tan phi. Moving on to the next slide. Over here, we have referred to a research paper from Mahmoud, where he prepares lime-treated clay soil samples, which is then subjected under triaxial testing machine. The graph on the right side shows how varying lime content affects the friction angle and cohesion values of the clay soil. For validation of the test in accordance with more Coulomb criteria, the deviatoric stress versus strain plot of triaxial test values observed is plotted and angle phi, that is the friction angle, is obtained from the slope, that is the tan inverse of the slope m. The tangent of this Morse circle gives us the 45 plus angle phi by 2. The sample clay soil in the first figure as observed from the test after triaxial test gives us the actual observed angle of the failure plane. This value is then compared with the theoretical value and is validated as per more Coulomb theory criteria. Moving on to the next slide. This is a quantitative analysis. The peak strength variation with lime content for lime treated clay soil. In here, we get Q equal to Q0 plus alpha AW into AW. This is from the research paper done by Martin Liu, in which Q0 gives as an untreated soil strength, alpha AW is material parameter, and AW max is the optimum lime content. The parameter alpha AW is a ratio of the maximum strength at optimum lime content to the strength of untreated soil normalized by the optimum lime content. The graph shows the variation between lime content and the shear strength of different types of soil, such as South Wales soil, sandy soil, and clay soil. Moving on to the next one.
Now we are going to discuss about optimum lime content. The graph shows a revised plot showing the simulated data comparing shear strength and lime content for boulder clay, which was obtained from Martin Liu's paper. This graph illustrates the relationship between shear strength versus lime concentration. We can see that there is an increase in strength with lime content until peak strength is achieved at optimum lime content. And with further addition of lime, we can see beyond the optimum lime content, reduction in strength is also observed along with the stiffness. It is obviously essential to identify the optimum lime content and the corresponding maximum shear strength referred to as AW max and Q max. In this case of boulder clay, the optimum lime content for peak strength, shear strength, reaches at 9%. Moving on to the next slide. From the research paper of Bell, optimum lime content of montmorillonite is 4%, kaolinite was between 4 to 6%, and quartz was ranged between 4 to 8%. The addition of small amounts of lime to these clay soils give rise to notable increase in unconfined compressive strength. The compressive strength of lime-treated soil develops rapidly with increasing addition of lime until an optimum lime content is reached, beyond which the strength begins to decline. Optimal lime content improves the strength of stabilized clay due to an increase in formation of cementitious compound, causing the cementation of the constituents. Therefore, increasing compressive strength, shear strength, and stiffness of the lime-treated clay soil. But if there's an excessive addition of lime, it does not have any effect on cohesion of friction angle due to excessive cementitial gel formation. So addition of lime beyond AW max is destructive and wasteful and should be avoided, because the purpose of any ground improvement measures is to improve the strength and the stiffness of the soil. Moving on to the next slide. After a comprehensive study of various research papers, we have tabulated peak strength versus optimum lime content for various clay soil. This is represented in this table. And for a better representation, moving on to the next slide. This study has been graphically represented for better understanding. So the lime content versus optimal lime content versus the peak strength of different clay soil from various research papers has been graphically represented in this figure. Okay, moving on to next slide for factors.
When we add lime to clay soil, its shear strength is affected by several factors. First, the amount of lime plays a key role. Generally, increasing the lime content up to a certain optimal level leads to a stronger soil due to a chemical process called pozzolanic reaction. Next, curing time is important. Longer curing allows for more chemical reaction between lime and clay, which further enhances soil stabilization. The type of soil and its mineralogy also matters, as different clay minerals can react differently with lime. Initial soil properties include moisture content, density, plasticity, and compaction influence how well lime treatment works. Finally, environmental conditions like temperature, moisture, and pH affect the rate and extent of lime soil reactions. Moving on to the next slide. There are some application of lime in soil stabilization, that is encapsulation of contaminants, highway slope stabilization, rendering of backfill, foundation improvement, and cost-effective alternative for soil stabilization. Moving on to the next slide. Clay soils mixed with low lime content tends to reach maximum strength faster than mixture with higher lime content. Generally, the optimal lime content to achieve peak strength, shear strength is between 3 and 8%. However, the relationship between lime content and strength is non-linear. Adding too much lime and can actually decrease the soil overall strength. The non-linear pattern suggests that while limes help stabilizing soil, it does not contribute a significant factor of cohesion on its own, making it crucial to find the right balance. Curing plays an important role in lime stabilization, with a rapid increase in strength during these first 7 days, followed by the slower but steady rise and depends on the time, temperature, and humidity. Moving on to the next slide. These are the references, and thank you.